Good morning or good afternoon, everybody, depending on what time you're watching this. We're doing the 2012 number 6 problem. I've already set up the ratio because it's asked for the ratio test for part A. So I set up the ratio of a sub n plus 1 over a sub n. Now I'm going to change this by multiplying by the reciprocal of the denominator. Whoa. There we go. So I'm going to multiply by, wow, I just realized I messed up, didn't I? Let me fix something here. Try to save some time, and it didn't do what I wanted. All right, that's better. So the bottom's going to be 2n plus 5. And then the reciprocal of the bottom is this. Now we're just going to start simplifying this. If you look at this and that, the top one has 2 extra x's in it. So when you cancel those, you're going to end up with the x squared. And then, if you're looking at this, the top one has an extra 1. So negative 1 to the n, to the 1. And now we can find our ratio. The ratio test says we take the r will be the limit as n goes to infinity of the absolute value of this. Don't forget the absolute value. So on top, we're left with a negative 1 x squared and 2n plus 3. On the bottom, we're left with 2n plus 5. Now, our variable that's changing, n, is going to infinity, so x is actually a constant. The negative 1 is insignificant since we have an absolute value, so I'm going to pull the x squared out in front. It's the rule of the limit. A constant can be pulled out, and we're left with this. So you can either divide top and bottom by n, or you can do L'Hopital's, but what you'll get here is this is going to be 1. So now we found r. So in the ratio test, if absolute value of r is less than 1, the series converges. But if it equals 1, it's inconclusive. If it's bigger than 1, it diverges. So we know our series converges on, or when, I should do when, absolute value of x squared is less than 1. Now when it equals 1, it's a different situation, so we'll have to deal with that separately. So I'm going to square root both sides, and that will leave us with x, absolute value of x is less than 1. Whoa. Then to rewrite this, it would end up looking like that. So that we know is a region of convergence, but it's not the interval because I don't know what's happening at negative 1 and at 1 because those are cases that makes r equal to 1. So I need to evaluate those separately. So we're going to let x equal negative 1. We're going to plug that down here into the general term here. Then we get this series. Negative 1 which equals So the top, you add the exponents. So it's going to be negative 1 to the 3n plus 1. Now the top, make sure it alternates. Since it's a 3n, it actually will. But if we had a 2n, it's not going to alternate. But this will, because you can test numbers. Put in 0, and you will get a negative. Put in 1, and you'll get a positive. So it does alternate. So your conclusion, since the terms alternate, and the terms decrease in magnitude to 0, therefore, this series converges. So that's the alternating series test for convergence. If it's alternating series and the terms decrease in magnitude to 0, that proves convergence for this series. Excuse me. Now we're going to try the right endpoint. And we're going to plug everything in. So that is gone because it's just 1. My brain is... Okay, I think we're good. It's weird. I was expecting one side to converge and the other not, but it looks like both are going to be the same. So we have a situation again where we're going to ditto all the top, because this again, if you look at it, it's an alternating series decrease in magnitude to 0. So ditto the top. Now, you probably shouldn't say that. I just did that. But I guess I could say, for the same reasons as the previous problem, this series converges. I'm not going to take the time to write that out. Now, after you get all that, your final conclusion, therefore, the interval of convergence is, and it'll be -1, including -1, inclusive, and 1. That's your final answer there. So the next two parts I think are going to be pretty easy. So part B, we're going to use the series they gave us at 1/2, and they tell us, this is important, this is an alternating series whose terms decrease in absolute value to 0. So that's given. And then the approximation is, this is the approximation using our series, two first terms. Showed that this approximation differs from the actual value by less than 1/200. So let's go through the steps. So the error is going to be the next term if we have an alternating series decrease in magnitude to 0. So I'm going to restate that because that is necessary for our answer to be correct. So since the series is an, now I'm going to write this all out, alternating series whose terms decrease in magnitude to 0. Therefore, the error, you can just write absolute value error. This case, I'm going to do this, the absolute value of this minus, okay, the Taylor series, actually, I don't have a symbol for Taylor series. The second degree, did it say? Let me read. Approximation, first two terms. The first two terms is actually a third degree Taylor polynomial. So I could do T3 at 1/2 for a third degree Taylor polynomial. But actually, instead of that, or, and this is probably better, easier, you have to worry about any of the little details. So that's going to be less than the next term in the series. And we don't have to maximize it because this is an alternating series. The next term is x to the 5th. So we're going to do 1/2 to the 5th over 7. And that hopefully is less than 1 over 200. So you could do that. 2 to the 5th power, what is that? 4, 8, 6, 32. 32 times 7 is definitely bigger than 200, so we're good. We have finished. Now, you have to check your book. I don't know. This here, I don't know if there's an equal sign there or not. I actually think it's no equal sign. I'm pretty sure, so I'm just going to leave it that way. I don't know if they're going to be picky like that on the actual test, but you might want to double check the alternating series test. That's chapter 9, section 6 or 7, if I remember right. All right, part C. Let's do that. And this is actually pretty easy. So part C, whoa, I don't want that. This was B. So this is one of the 5 things you can do to a Taylor series. You can take the derivative. And so if we are given G is our original function, here's the original Taylor gave us. The rule says the derivative of the function on the left is equal to the derivative of the individual terms of our Taylor series, and they want the first 3 non-zero terms and the general term. So the general term is going to be this. So the first 3 terms are pretty easy. Use the rule. Wow, that's a x. There's not a cube there. What's the derivative of x over 3? It's just 1/3. Here you bring the 3 in front, decrease the power by 1. Here you bring the 5 in front, decrease the power by 1. Now, here's the part where you have to kind of think a little bit. This is a constant. Okay? So, because the reason to get the first term, let me show you for those of you who didn't quite see this. To get the first term, you plug in 1 into the general term, and you will get the first term. So n's a constant for that term. For the second term, you plug in, no, I lied to you. This is 0, sorry. Plug in 1, and you will get the second term. For the third term, you plug in 2. So n is a constant for each individual term. So if you want to take the derivative of this, you have to consider each time you take the derivative, n is a constant. The variable is your x. So you should know whenever you have a constant, all you do is copy the constant down. And then you have x to a constant. What's the derivative of x to a constant? You all know you bring the constant in front and you decrease the exponent by 1 and the bottom stays the same because that's a constant. Okay, so everything highlighted there are constants. So that's the general term. And that's my work. I'm done. That one was actually, I thought it was pretty easy. Hopefully you also. All right, there we go.